Hello, chemistry students. This is lesson one of our mini unit on gas laws. This semester we will not actually get through all the gas laws content, so just trying to introduce y'all to some of the big concepts from the gas law standard and elements. So today we're looking specifically at element 5C, which is the relationship between pressure, volume, temperature, and number of moles of a gas. Normally, if we were face-to-face, I would do some demos at the beginning of this unit to kind of kick it off, but since we're not, I'm going to show a couple of video clips of the demos that I would typically do. So, one of the first videos is of a Cartesian diver. It actually walks you through how to make it. I might even still have mine on campus at school. So what I'm wanting you to notice, he built the Cartesian diver, which is not a big deal, but I'm wanting you to notice what happens to the little eyedropper as he squeezes the bottle, and then what happens to the eyedropper as he releases the pressure on the bottle. So right now, I've currently paused it in him in the process of squeezing it. So notice when he releases the pressure, the Cartesian diver comes back up. When he applies pressure, the Cartesian diver will actually go down. This is one of those few things that I can actually say, yes, this is safe for you to do at home. If you have an eyedropper or something similar, you can actually also do it with some clay and a pen cap. But get yourself an empty bottle and fill it up with water and put some type of a dropper in it. It's hard to really see in this particular video, but if you were looking at it in person, you would notice that as he squeezes the bottle, the little bubble that's in that eyedropper, that air bubble there, actually shrinks. It gets smaller. So we're going to talk about why that happens as part of this unit. The next demo that I would typically do is this one.
Guys, how you all doing? Easter is coming up, so happy Easter, and I thought might as well put peeps in the vacuum and we'll see what happens. We got a few peeps over there. Let's turn the vacuum chamber on, suckle the air out and see what happens. Wow.
So notice this is a vacuum chamber. They are literally pulling the air out of that rigid glass container. Notice what's happening to the size of the marshmallow peeps as they are removing the air from the container.
Wow, would you look at that? This is so cool. Look how much bigger they are. Wow, they actually...
And also notice what happens to the peep once they stop removing the air and they actually put the air back into the container.
Imploded. Look at this. Oh my goodness. Look how much smaller they are. Look at this. This is what it used to look like. Now this is what it is. It's just imploded inside of it. Pretty crazy, huh? So if you break it apart, there's no bubbles inside of it. It's pure marshmallow. Pretty.
So it's kind of neat. He didn't actually show it next to the enlarged marshmallow peeps, but they do like almost triple in size if you are able to get a complete vacuum going. So notice how the volume of the peep changed as the air was removed, or the air pressure was removed from the container. So the last demo I would typically do, and this is one that's always fun in class, is the imploding can demo.
Show you how to implode a can using atmospheric pressure. Start by filling a container halfway full of ice, and then add water until it's all the way full. Add about a tablespoon of the water to an aluminum can, and then place this can on a hot plate. Turn the hot plate on high, and wait for steam to be pouring out the top. At this point, your can is ready to be imploded. Remove the can from the hot plate using tongs, and then in one motion, pour out the rest of the fluid and submerge the top of the can in the ice water. The can implodes because as the steam condenses back,
don't want him to explain it because I want us to kind of learn about the gas law that is causing the can to implode. But this only works if you're actually able to get the water or the steam in the can hot enough, and you can get the mouth of the can into the ice water fast enough. So if you don't have enough ice, or if the can's not hot enough, this is something that won't always work. If you have adult supervision and some tongs or even like oven mitts, this is again one that's kind of sort of safe to do at home. I would definitely have some adult supervision so that you don't accidentally burn yourself. But yeah, we've got, notice what happened to the volume of the can as the temperature of the gas or the temperature of the stuff inside the can changed. So, starting with a little bit of gas law, kind of just some basics about gases. And sorry, I did not mean to clicky through that, but there we go. So, gas pressure. I mentioned this term a second ago. Pressure is the result of the forces exerted by the gas per surface area. So right now in your body, you have air molecules hitting your body all over your skin. They are exerting a certain amount of pressure on your body. Gas pressure is the result of all of those collisions all happening, randomly occurring over time. When you're thinking about like a basketball or a football or maybe a bike tire that's low on pressure, it's because there's not enough gas in there to kind of put enough force to keep the object inflated. Now, the benefit of the vacuum chamber is a vacuum is a space where you're actually able to remove all of the particles. There's no gas particles in a vacuum chamber once it's all been removed. And if there's no gas particles, there's no pressure. So those marshmallow peeps, when they got really, really big, basically the pressure was really, really small. I don't want to say it was exactly zero because odds are he probably did not take it that strong. So there are some tools that scientists use to measure pressure. Some of you, if you have some older parents or maybe even grandparents, you may have seen something like that in your house. It's called a barometer. And it actually measures the atmospheric pressure. The way it used to work is quite literally the air would be pushing down on a liquid. And the liquid would end up being forced up a tube. The more the air pressure, the higher up the tube the liquid went. The liquid was specifically mercury. So one of the earlier units for pressure was millimeters of mercury. Now, interesting thing about the Earth as a whole. The higher up you are, or the higher your elevation, the less gases that are pushing on your body. The lower your elevation, the more the atmospheric pressure is on your body. So if you're at sea level, most of the Earth, sea level, the gas pressure is 1 atmosphere, or, 760 millimeters of mercury. But a barometer is a device that's actually used to measure atmospheric pressure. When the weather guy or gal says that, hey, there's a high pressure system coming in or a low pressure system, they are using some type of barometer outside a building nearby to measure the air pushing on a sensor in that device. Now, like I mentioned earlier, the first units of pressure were literally millimeters of mercury. But we since learned that mercury is very, very toxic and we don't really want to be exposed to it. So we now use nice fancy equipment to measure pressure. And usually it's measured in kilopascals, kPa, or atmospheres. So 1 atmosphere, so 1 ATM, That does not stand for automatic teller machine, but it is short for atmosphere. 1 atmosphere equals 101.3 kilopascals. It also happens to equal 760 millimeters of mercury. It's like these are all related. They're all equivalent values. It's kind of like saying there's $4 in a Batman's range. There's 4 quarters in a dollar, and there's 10 dimes in a dollar. Either way, you still got $1 worth of stuff. Now, unfortunately, you know, the U.S. has got to be a little bit weird. Generally, when we are measuring pressure, we measure it in pounds per square inch. That is why you probably are familiar with PSI. If you have ever had to help your parents check the tire pressure, that little doodaddy that lets you know how much is in PSI, pounds per square inch. But this is science. Yes, I know we're in the U.S., but we still got to use scientific units. So we typically will not see PSI. We will see kilopascals, atmospheres, or millimeters of mercury. So way back with Unit 1, we learned about the nature of gases, and we learned a little bit about the kinetic molecular theory of gases. So that theory basically explains the motion and the behavior of specifically gases. Now, every object is constantly moving. The atoms in it are constantly moving. It doesn't matter whether it's a solid or it's a liquid or a gas. The more the particles move, the more kinetic energy they have. The more kinetic energy they have, typically the higher the temperature is. Now, the kinetic molecular theory states that matter consists of tiny particles that are in constant motion. So remember back at the solid phase, that motion was just vibrating. When they went to the liquid phase, they were able to slide past one another. And when they finally get to the gas phase, they're like ping pong balls bouncing all over the room. Those little particles are moving very, very quickly through the space that they're in. So, kinetic molecular theory is essential for explaining why we are able to compress gases, why gases mix at different rates, as well as what gas pressure is. So I'm hoping some of you have seen this particular object before. This is, I think, a generic version of it, but it's canned air. It's used to clean your keyboard, and it's literally compressed, really, really smushed together gas particles. When I squeeze the little nozzle, you hear the noise, but you don't really see anything coming out. And that's because it's literally just sending gas into the air. If I had a brand new bottle of this and I was shaking it, it would sound like there's a liquid in there. Well, that's because we have compressed that gas so that instead of the particles being really, really far apart, they're now close together. And if we get particles too close together at too high of a pressure, we can force something to turn into a liquid that is not normally a liquid at room temperature. Now, we do, in order for the kinetic molecular theory to work all the time, we do have to make some assumptions about gases. And this means most of the gas laws that we're talking about will work the majority of the time, but there are a few situations where they don't work. Those situations happen to be at fairly low temperatures and fairly high pressures. But what the kinetic molecular theory says is that gases are really, really small, hard spheres, and their volume is insignificant to the volume of the object that they are in. So the volume of the gas particle doesn't really matter when we're considering the volume of the object itself. Those gas particles don't have any attraction for each other. Even though they are bouncing all over the room, they will interact and hit off of each other. There's not any attractive forces. Additionally, we have to assume that the motion of one particle is independent of all the other particles. Now, these assumptions are usually true under 99% of the situations. But when we get to a situation like my canned air, the gas laws won't work because the pressure's too high. So, the motion of the particles is rapid, constant, and random. This is what allows gases to fill up the container and occupy its entire shape. The gases are going to travel in a straight line until they either hit against a wall, another particle, or another object. Once they hit that object, it's like ping pong balls or bouncy balls bouncing off the wall. They're going to hit it and kind of elastically bounce back in the opposite direction. Now, we do have to assume that all of these collisions are perfectly elastic. That basically means that no energy is lost. So even when one particle hits another particle, they don't transfer any energy between them. Now, these assumptions work except when you're near a phase change point. So if we happen to be near the condensation point for that gas, there's going to be a lot of attractions going on and my gas laws won't work. If we happen to be at extreme pressures and that gas is being forced into a liquid, this won't work. But most of the time, we're not doing that. So compressibility is the ability of a gas to basically take up less space. We can change the volume of a gas by increasing the pressure. We can increase it so much that we cause the gas to turn into a liquid. The reason we're able to compress the gases is because the particles are really, really far apart. Typically at room temperature, so we're saying roughly 25 degrees Celsius or 75, I think, 75 degrees Fahrenheit for, us US folks. But roughly room temperature, the distance between a particle and a gas is 10 times the diameter of the particle. So what that means is if my gas particle is that big, then its next closest particle is going to be no closer than 10 times that. And if we increase the temperature, that distance between the particles change. So there are several things that we can do to impact the properties of gases. As we saw in the demos, if we change the temperature, we can impact the volume. If we change the pressure, we can impact the volume. If we, I forgot the third one. If we change the volume, we can impact the pressure. Additionally to changing the pressure, temperature, volume, you can also change the way the gas behaves by adding more of a gas, by increasing the number of particles. So, if I increase the number of particles, I'm going to increase the gas pressure. That kind of makes sense. Anybody who's ever played basketball knows that, hey, if you add air to that ball, whatever, it's going to become bouncier. There's more gas in there pushing against the inside of the basketball, and it's increasing the pressure. If I don't have enough gas molecules inside my basketball, it's not really going to bounce. It's not going to be inflated because there's not enough pressure. Now, in a rigid container, doubling the number of atoms of the gas will double the pressure. That means there is a direct relationship between the number of moles, and that is usually abbreviated with an N, and the pressure of a gas. Pressure is abbreviated with a P. So if my number of moles of the gas increase in a rigid container, that pressure will increase. So even though technically a basketball isn't really rigid, you get to a certain point, yes, it will explode, but it's a good kind of visual of this. As we add more air to the ball, it gets firmer and firmer, and that's because the pressure is increasing and increasing. If we lose air from the ball, it gets less firm, it starts going flat, and that's because the pressure is decreasing. So that is a direct relationship. Now, in addition to changing the number of molecules, we can also change the volume. So if I reduce the volume of a container, we will increase the pressure. So if the volume increases, pressure will always decrease. We get a larger container, that means there's more space for the particles to spread out and have to hit the wall, which means there's going to be less interactions with the side of that container. So where earlier doubling my number of particles doubled the pressure, well now if I double the volume, I'm going to increase the pressure by half. And this actually kind of says the exact opposite, but it's the same idea. I cut my container in half and I doubled that pressure. So that's that opposite relationship. If I increase the volume by a factor of 3, that means my pressure is going to decrease to a third of that original value. So they are inversely related. Now, note that if the volume and the number of atoms are constant, so I'm not changing the volume, I've got a rigid container, I'm not adding more gases, then pressure is related to temperature. And in fact, pressure is directly related to temperature. So if we double the temperature, and the temperature must be in Kelvin, if we double the temperature, we're going to also double the pressure. So this is saying that, hey, my volume and my number of moles are constant, which means they don't change. So if the temperature increases of a container with a gas, that pressure is going to increase. If you've ever went from a cold environment to a warm environment on a long road trip, you've seen this. Your tires get hotter, the pressure increases. The opposite is true. If the temperature decreases considerably, the pressure will decrease. So what that means is if my temperature decreases by half, If my temperature decreases by half, that means my pressure is also going to decrease by half because they are going in the same direction. So one of the things you're going to want to make certain that you have in your notes from this is how changing one factor affects the other for a gas. We will see each of these in a little bit more detail as we are working our way through the gas laws, but think about the demo at the beginning. As the pressure was constant on that one, sorry. So my marshmallows would be an example of this top one. That pressure went down a lot. It went down like a bunch of times. And the volume increased considerably of the air that was inside the marshmallow. Well, if the volume inside the air in the marshmallow increased, that's what caused the marshmallow to get bigger. And it got so big that some of that air escaped from inside the marshmallow and ended up getting sucked out of the vacuum chamber, which is why when we let the air back in, the marshmallow looks so much smaller. So remember back to Unit 1 that temperature of a substance is a measurement of the average kinetic energy. So if we increase the kinetic energy, we're going to increase the temperature. If we are cooling down a gas, we are removing some of the kinetic energy. We're going to cause those particles to move slower. If they're moving slower, their temperature will be reported as a lower value. Now, for gas laws, temperature must be in Kelvin. So you may or may not remember this from math in middle school, but I promise you've seen this either in math or science before. To go from Kelvin to Celsius, Kelvin equals my temperature in Celsius plus 273. For the most part, even though America uses Fahrenheit, we're not going to see Fahrenheit on my problems. You're going to see Celsius, or you're going to see Kelvin. So if getting to Kelvin means I have to add 273, if for some reason I'm wanting to know the temperature in Celsius, then I just have to subtract. Kelvin minus 273 would give me my temperature in Celsius. And I think we're going to see that again in a second. Now, when we're talking about gas laws, you will frequently see the phrase standard temperature or standard temperature and pressure. And that gives you a lot of information about the situation that the experiment's being conducted in. So, standard temperature and pressure, remember back when we learned about STOIC, we assumed anything that dealt with gas was at STP. Well, we can't make that assumption anymore, but if the prompt tells us that we have standard temperature, standard pressure, or standard temperature and pressure, it's telling us some specific numbers in word form. So, standard pressure is 1 atm or 103 kPa. I knew that didn't look right. 101.3 kPa. So 1 atmosphere and 101.3 kPa, those are equivalent values. It's okay. Standard temperature is 273 degrees Kelvin or 0 degrees Celsius. That is the same numbers. So anytime a prompt says, hey, you have standard pressure, you've got 1 atm or 101.3 kPa. Anytime it says you have standard temperature, it's saying you got 273 degrees Kelvin. When we're looking at gas law calculations, you absolutely positively must make certain your temperature is in the right unit. So if the temperature is not in the correct unit, you're going to have to do a conversion. Same thing with the pressure, but we're less likely to see that, at least definitely this semester. But you will see me giving you the temperatures in Celsius, and you are expected to convert it to Kelvin. So let's look at a couple really quick examples. And before we get to the examples, this last little bullet, these values are on your cheat sheet. They are on your periodic table, so you do not need to memorize them. But they at a glance tell you what your STP, what the P part of standard temperature and pressure is. It tells you that 1 atm or 101.3 kPa. So let's look at a couple real quick temperature conversions. I'm telling you that the temperature is 25 degrees Celsius. I want to know it in Kelvin. What do we got to do? We just got to add 273. Easy peasy lemon squeezy. Sorry about that. Oops. So, my Kelvin, let's say for some reason we've gotten the answer in Kelvin, but we need to know it in Celsius. Then if I'm going from Kelvin to Celsius, I just have to subtract. The K equals degrees Celsius plus 273 is also on your formula sheet. So 0 Celsius, that is how we know that at standard temperature, 0 Celsius is 273 degrees Kelvin. So it is possible to have negative temperatures in Celsius. It is not possible to have negative Kelvin. The Kelvin scale is based on absolute zero, which means literally 0 is the absolute coldest that you can get on that scale. But in Celsius, yes, you can get negative values. So, I am going to start our gas law discussions with the combined gas law. it combines together 3 out of 4 major gas laws that we will see this semester. It's also the major kind of calculation that we see in gas law type problems. So, the combined gas law assumes that you have an enclosed gas. So, an enclosed gas is implying that the number of moles is constant. So, the amount of gas is constant. Remember, N stands for number of moles. So, it allows us to see the relationship between pressure, temperature, and volume of any gas. It allows us to do calculations where only the amount of gas is constant. Now, emphasizing that in order to actually use the combined gas law, your temperature must be in Kelvin. I cannot say that enough. You've got to have the temperature in Kelvin, otherwise the calculations won't work. So, this is, in my opinion, the ugly version of the combined gas law. P1 times V1 over T1 equals P2 times V2 over T2. It's given to you on your formula sheet, but I honestly prefer the linear version where we've cross-multiplied and it looks, there we go, like that. So, all of the ones are initial values. So, initial temperature, initial pressure, initial volume. All of the 2's are your final values. Notice that when I cross multiply, my equation turns into P1 times V1 times T2 equals P2 V2 times T1. So the T's are a little bit wonky. But the benefit of that version of the equation is when you are trying to solve for an unknown, all you have to do is divide by the other stuff on that side of the equation that you do not want. So it makes the algebra a little bit easier. So with this linear version of the equation, let's say a problem is asking me to solve for T2. So in order to solve for T2, I'm going to divide both sides by the things on the same side of the equation that I don't want. So T2 ends up being P2 V2 T1 divided by P1 V1. Like I said, it makes the algebra a lot easier. It works with any of them, doesn't matter. Let's say my prompt's asking for V2. Okay, well, I don't want V2. That means I got to divide both sides by what's on that side. So I copy everything on the other side, P1, V1, T2, and then I divide by my P2 and my T1. So this makes the algebra a lot easier. What gets a little bit complicated with these problems is figuring out what is your initial and what is your final. And unfortunately, that's where the words and the problems are going to matter the most. So let's look at a couple of examples. I have a gas that takes up a volume of 15 liters and has a pressure of 4.3 atm and a temperature of 299 Kelvin. If I raise the temperature, raise, that word is implying that we have changed something. So if I raise the temperature to 350 Kelvin and lower the pressure to 1.5 atm, what is the new volume of the gas? So we've got to figure out what everything equals. So find all of your numbers and assign them to each particular variable. Now remember, volume is typically measured in liters or milliliters. Temperature is typically measured in degrees Celsius or Kelvin. Pressure is typically in atmospheres or kilopascals. So the unit tells you a lot about it, even if we don't have the extra words. The fact that that says liters is telling me that this is my volume. The fact that this says ATM is telling me that this is a pressure, and that has Kelvin is telling me that it's a temperature. Now, the way I know if it's a P1 or a P2, is it initial or final, is the extra words. So that raise the temperature is saying that, oh, this is my final temperature, so that has to be my T2. Which means all the other things that I've identified had to all be ones. So notice a good strategy for solving these type of problems is to quite literally list the information that you were given in the problem. Once you've listed your information, verify that your temperature is in the right unit. It is. So now we can actually go through and rearrange the equation to solve for V2. So I'm trying to get V2 by itself. That means I'm going to divide both sides by P2. It's gone there. And T1. It's gone there. Now I can just plug and chug the numbers. So P1 is 4.3 ATM. V1 is 15 liters. T2 is 350. Make certain that it's the T2 on top for this problem. Divided by P2, 1.5 ATM, and T1 on bottom, 299 Kelvin. So if I look at my units, I can see that with my units, ATM is gone, Kelvin is canceled out, and we are left with liters. Well, the problem is asking me to find volume. The units and my prompt kind of agree. So I plug those numbers into the calculator, and it gives me an answer. Now, for some students, they prefer to plug the numbers in before they rearrange the equation. I don't care. I really, really don't care. It's whatever makes the most sense to you. So either one of those would be correct ways to show the calculation for V2. Now, for those who are like, how do we type this into our calculator? It would look something sort of like this. This is why I really, really love the Desmos Scientific. So my personal preference was always to rearrange the letters and then plug the numbers in, because I had issues flipping numbers up. But it really doesn't matter as much. So, where'd it go? Okay, there we go. So, we're typing this in. I need my fraction button. I got 4.3 times 15 times 350. Clicky down to the bottom, or arrow down to the bottom. 1.5 times 299. This is the nice thing about this is it's once you figure out where everything goes, it's plug and chug. Now, one thing that does not necessarily apply to this problem, but we might see, is you also have to make certain your volume is in the same units. So for some reason, it was asking me for milliliters. I would have to do that conversion. It's not, so I'm not going to worry about it. All right, let's look at another gas law problem. We're going to ignore the fact that little extra line's down there. So a sample of gas occupies 45.5 liters at STP. What temperature must it occupy to have? What temperature must it have to occupy 26.5 liters at 2 ATMs? We'll put that unit beside the number. So you have to remember, anytime you see STP, those are numbers hidden in the words, or hidden in the letters. Standard temperature, standard pressure. My standard temperature is 273 degrees Kelvin. My standard pressure is 1 ATM, or 101.3 kPa. Well, since my other unit for pressure is ATM, that's the one I'm going to use. So, what temperature must it have to occupy that information? These two numbers are really, really close proximity in the problem together. That means they are probably both the same subscript. In this particular situation, they are both 2's. So they are my V2 and my P2. And it is asking me to find my T2. Notice how 45.5 liters is in close proximity to that STP. That implies that those three things go together. So that is my initial volume, my initial pressure, and my initial temperature. I don't know why I did T after V, but whatever.
What are you doing?
So, check our units. Do we have Kelvin? Yes, we do. Do my units match for pressure and volume? Yes, they do. It is asking us to solve for T2. So I want T2 by itself. That means I got to divide both sides by P1 and V1. Now, yes, you could just plug all the numbers in and use algebra and some math to solve for T2 that way. My personal preference is to rearrange the letters and then plug and chug into the calculator. But notice with this version, I can easily see that, oh, ATM is divided by ATM, it cancels. Kelvin's divided by Kelvin, it cancels. And we should be getting a temperature. What happened? Oh, that shouldn't be a Kelvin. 45.5 should be a liters. Bad copy and paste, Miss Rains. So the liters cancels with liters. And we should be left with Kelvin. How did I know it had to be Kelvin? Well, it's asking for temperature. So that's a benefit to writing those units with those numbers, is they can help you catch mistakes. Okay, yay, good. So, third example, I believe this is my last example for today. I've got a 5.65 liters of a gas at 25 degrees Celsius in 1 atmosphere. What volume will it occupy at 1.5 atm and 50 degrees Celsius? So, numbers that typically are in close proximity in the problem tend to have the same value in terms of the 1's or the 2's. Are they your initial or your final? So this is asking me for volume. I'm going to assume that it's V2, which means this has got to be my P2 and my T2. Yes, sometimes your final values are given to you at the beginning of a word problem. Not very often. The main thing would be to figure out what variables are all linked together, what numbers go to the same situation. So my initial volume, my temperature. Notice it is in Celsius and I can't have Celsius, so I went ahead and right away converted it to Kelvin. Same thing with my T2. I went ahead and right away converted it to Kelvin. Because all temperatures must be in Kelvin for gas law calculations to work. They don't work with Celsius. We can't deal with those negative values. So we're asked to find V2. That means we need to divide both sides of the equation by P2 T1. Notice atmospheres divided by atmospheres, it cancels out. Kelvin divided by Kelvin, it cancels out. We are left with liters. Liters measures volume. So the units and the numbers should agree. So as y'all are working through your practice for combined gas laws, on the guided practice, one of the first things I will have you do is just practice identifying, is it an initial number or is it a final number? You do want to make certain that you have down in your notes that volume is liters or milliliters, temperature is Kelvin or Celsius, and pressure is atmospheres or kPa. And that will help you a lot when you're working on these problems. That is it for today. Remember, come to the office if you need assistance with this content.